Hello class, this is Calculus Part 4. In this video we'll be looking at differentiation by first principles. Bringing all the previous concepts together, we will finally answer the question, what is the gradient or the rate of change of a curve? We're going to do a slight adjustment to our understanding of the gradient formula. So we already know that the gradient is calculated using y2 minus y1, or just the rise over run. Instead of just thinking of two separate coordinates, we will consider the x values as some distance from one another and the y values as function values. So for example, if we wanted to find the gradient of these two, we would do 7 minus 3 divided by 2 minus 7. But instead of thinking of this as 2 and 7, instead think of the x values as some distance apart. So the distance from 1 till 2, so from 1 until 2, is a distance of 1. And the values of 3 and 7 are just the function values f of 1 and f of 1 plus 1, because remember it's 1 plus 1. In general terms, so instead of using actual numbers, we can just say it's x1, y1, x2, y2. Instead of x2, y2, let's think of it as x plus some distance h. So this x value is x plus h. The function, the y value, y1, is just f of x. And the y value of y2 is f of x plus h. Okay, so now by reapplying the gradient formula, we arrive to this new formula. So the gradient is, going along here, y2 minus y1 over x2 minus x1. So really honing in on this, y2 minus y1 over x2 minus x1. Evaluating this, x minus x, so these two cancel, leaving us with just this form here. Using this new form, we can easily calculate the gradients of a secant of any function or curve. So this point is x, f of x, and this point is some distance away, so some distance away, x plus h, and f of x plus h. Same goes for this one. We have a point x, and this point is some distance away of h. Its y values are f of x and f of x plus h. Also using this form, we can calculate the gradient of a tangent by turning a secant into a tangent. This was done by moving one point of the secant closer and closer to the tangent. So here's a little demonstration again. So let's say that this is a distance of 1. Bringing it closer and closer, the distance is now half. Distance of 0.1. And eventually, once the distance of these two becomes 0, this point becomes the first point. So that becomes the tangent. Here's another visual example of this. We have 2 points, x plus h. Letting h become closer and closer, so it's moving this point closer and closer. There it is, it's moving closer. And eventually, it becomes the same point where the distance of h is 0. What we're actually seeing here is a limit. More specifically, we are calculating the gradient of a tangent by letting h approach 0. So if we have here the gradient, so if we were to calculate this gradient and let h approach 0, so it gets closer and closer, that point moves closer and closer, and it becomes the tangent. Comparing this to what we previously saw, we actually let the 2 points be some values, but rather than be 2 different values, I want you to imagine that the distance between the two is actually approaching 0. So they're getting closer and closer. So in summary, we're moving this point here. Let's say it has a distance of 1. Once we move the distance to 0, the point becomes the same point, resulting in the tangent, giving us the tangent m equals 2. So this example calculates the gradient of the tangent only at this point, and only for the function shown here, so only for this particular curve. But this process will work for a tangent at any value of x for any function or curve f of x. So to answer the key question we've been leading up to, what is the gradient or the rate of change of a curve? To answer this, the gradient of any curve or function is the gradient of any tangent drawn along the curve. To calculate the tangent at any point x, we use this formula here. I'll show you how to read this. This is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is what's known as differentiation by first principles. If you're wondering, differentiation, this word here, simply means find the derivative. Find the derivative. Now, this raises a few more questions. What is the derivative? Oops. So, this symbol here, f prime of x, is known as the derivative. It is a function that calculates the gradient of any tangent along the curve f of x. To really drive this home, let's do one example here. Let's calculate the derivative of the function f of x equals x squared. So here's the drawing here. So let's do this. Whoops. Utilizing this here. Let's duplicate. So for this, we actually need 2 sub functions. We need f of x plus h. So f of x plus h. This means in this function here, here is x squared. So this is x squared, like so. But instead of substituting a number like we normally do, so 1 or 2, we're going to substitute x plus h. Expanding this, this becomes x squared plus 2xh plus h squared. And we have f of x. F of x is just x squared. Now, using this derivative, we can using this formula, we can find the derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h is this form here. So let's move this here. So instead of this, we're going to substitute this expression. So it's going to become x squared plus 2xh plus h squared. So that's this done, minus f of x. Well, f of x is just x squared all over h. And now we need to apply the idea of a limit. The limit here, before we actually substitute h equals 0, we need to factorize and collect any like terms. So take a look. X squared minus x squared. That cancels. This leaves us with the limits as h approaches 0 of the remaining expressions are 2xh plus h squared over h. Again, before we substitute h equals 0, we need to factorize. So on the top, we can factorize h. So the limit, as h approaches 0, it becomes h on the outside, 2x plus h all over h, cancelling like terms. Continuing here, we get the limit as h approaches 0 of 2x plus h. Well, now if we let h approach 0, this just becomes 0. So what we're left with is 2x. So the derivative of f of x equals x squared. F prime of x is equal to 2x. And I'll demonstrate to you what this actually does. Let's create some more space here. Now, using the derivative, let's calculate the gradient of the tangent at x equals 1. Visualizing this first, what this means is we're going to go to x equals 1. So let's say it's about here. We're going to now go up and draw a point there. And at that point, we want to draw a tangent. And now, in order to measure the gradient of this tangent, we actually just use the derivative. So the gradient of this tangent here will be, well, we have this, f prime of x is equal to 2x. So now substituting x equals 1, we get f prime of 1 is equal to 2 times 1 equal to 2. So the gradient at this point here is 2 and 1. So the gradient of this tangent is m equals 1. Let's do another example. At x equals -2. Again, what this means is along the curve here, we find x equals -2. We draw that point, and we draw a tangent at that point. Well, now we're going to measure the gradient of this tangent. Well, to do that, we use the derivative, f prime, substituting -2 into the derivative. It becomes 2, so 2 outside of -2. So the gradient of this tangent that we've just drawn here, the gradient of this is -4. One last example. Whoops. At x equals 0, So what's going on here is we find x equals 0. We draw a tangent at that point. That's probably not properly drawn, but whatever. Now, to find the gradient of this particular tangent, we use our We use our derivative. So f prime of 0 equals 2 times 0. Well, that's just 0. So I hope that really gave you an insight into the foundations of differential calculus, and you understand how we found the derivative and that it calculates the gradient of a curve at any point. Hope to see you in the next video. Best of luck.